Hello dear everyone, my name is Andrei Lee, also known as Andrei Lee PhD. Today I'm going to be explaining backpropagation. It's a very simple concept but requires some attention, and probably you browse through some materials and you have questions how it is really working. What is the kind of a live example with code, because many things are hidden in API of different frameworks like TensorFlow, PyTorch, and Keras. Especially for TensorFlow and Keras. Keras, for example, compiles your model, and there is nothing live. But PyTorch is doing everything live, so you can track everything, how the gradients are calculated, and many other things. So I strongly recommend you to use PyTorch as your neural network framework, because it's really cool. It's really extensible. It's really pleasant to use. So, and probably you know the theory behind neural networks and know a little about backpropagation. So let's move forward to the example. So here I have a neural network, and we have 3 input neurons that are axis. So this is our input neurons. This is our layer. As you can see, it's wx plus b. This is linear layer in PyTorch. And then we move to the output and then loss function, where we are all calculating. So everything is pretty simple. So there are 2 main processes that are happening in neural networks. So first, it's forward propagation and back propagation. Forward pass is pretty simple. It's just a simple school math, and back propagation is also, I would say, school or college math. Really simple, and you will understand it perfectly if you listen my webinar. So let's move forward to the forward propagation. So it's pretty simple. We have x, we have a linear layer. So x goes to the here, and we have a nice formula wx plus b. So w is weights, b is bias. So x multiply by weights that are initialized randomly, some numbers, and we are in process of forward and back propagation. We are adjusting this number w. So then we are use a ReLU activation function that is simply the number if a number is positive. For example, 3 is just 3 after ReLU, and 6 is 6 after ReLU, but if number is negative, it's 0. So if you have -3, the output of ReLU would be 0. Then we have output where we are doing nothing. We just kind of consolidating our data. And what is here? Then we go to the loss. What's the loss? It's a difference between output and target. So here you have a target. It's a supervised learning. And for example, here you have, for example, like grades in math, physics, and other subjects. And then we have a like target. For example, let it be 1 for the simplification. 1 is your ultimate knowledge, so you're kind of very proficient if it's 1. So we go here, we calculate, we have some numbers, then linear layer, then output, and we have an output, for example, 0.7. So we have 0.7 minus 1. It's minus 0.3. Then we square it, it's our loss. So this is the forward propagation. It's a pretty simple concept. So everything's clear here, and we move to the back propagation. So what do we do here? First of all, we have a loss. Okay, and we are going back using chain rule and derivatives and chain rule. So it's a pretty simple concept. For example, we first step, we moving from the right to left. We take a derivative of loss, which is 2 multiplied by loss, 2 multiplied by output minus target. So it's here gradient 2 multiplied by loss, because it's like a x squared, and derivative of x squared is 2x. So everything is simple. We have a loss, for example, some number. Then we move back here. Here we are doing nothing. There is no activation function, nothing at all. So we are kind of moving to this step. So first we encounter is a ReLU, and ReLU applied to Wx plus b. So first function that we are facing is ReLU. What is derivative of ReLU? It's a 1 if you have a positive value and 0 if we have a negative value. So for example, we have a positive value and we multiply it by our what we get here, like we calculated derivative, which is 2 multiplied by loss, and 2 multiplied by loss we multiply by 1 because derivative ReLU 1. And then it's this step. We kind of divide all this kind of thing into categories, like output and input. So first output, it's applied ReLU, and on input we doing Wx plus b. So we handled ReLU, and then its chain goes forward. So we dealt with ReLU. It's a derivative of 1 if we have positive numbers, and we have positive numbers in our example. So then we are facing this issue. So Wx plus b, what's the derivative of Wx plus b? And from the college or school or university, you know that it's W. But I want to mention that we are taking derivative with respect to W. So we kind of want to know the limit of this value. So, and the correct number, if you're like studied in university, Wx plus b derivative is simple W. If you taking it with respect to x, but if you taking it with respect to W, it's x. So derivative is x. Plus b is constant, so derivative on constant is 0. So we are left with x. X is our gradient, because here's the explanation, because derivative of Wx plus b with respect to W is x, and we have a gradient of our parameter. W is in PyTorch is a special type, torch.nn.parameter. So this parameter we are tuning. And for example, when we are using optimizer.step, we use optimization function. For example, stochastic gradient descent. It's very simple. This update is W, our weight, plus minus learning rate. For example, it might be 0.001 multiplied by x. Why by x? Because it's a gradient. We are taking this gradient, we calculate the derivative here, and everything is perfect. So it's x. So W plus minus learning rate multiplied by gradient with respect to weight, it's x. So we update our weight here. So, and this is a pretty simple example. We are not going here because we are completed our back pass. And let's move to simple example that I am going to present you with PyTorch. So very simple, even simpler than this. So let me close this window and move to another one. So this neural network is very simple. 3 inputs, 1 output, where we apply linear layer without bias, even no bias. So what we are doing here, we are doing back pass. There is no loss here. I just cut it out to simplify as much as possible. So we are calculating loss. Then we are using optimizer zero grad. Our optimizer, instantiated optimizer. We use optimizer detail zero grad. As you see, it perfectly fits with my example. And then we update zero the gradients here. Loss backward, we calculating gradients. And optimizer step, its update torsion and parameter is W. So it's updated here. So let's have a close look what's happening. So first we import torch. We make torch tensor of 0, 1, 0, 2, 0, 3 as in our example. Like here, it's strongly following this. And then we reshape tensor to 1, 3. 1 is a batch, and 3 is our another shape. Okay, name tensor is not defined because I haven't executed this cell. So defined, we see the tensor. This step we skip, and this is my neural network. So here's pretty easy to understand. We use one linear layer with 3 channels, 1 output features, and then we define forward behavior. Then we instantiate our model. We are looking at parameters of the model. So it has one parameter, weight, that has been instantiated to these parameters. Then we are checking that linear layer calculations. So parameter 0 is our parameter, weight. We use matmul option and multiply x by our parameter to check. It should be 0.0847. Then we check shape, use our model, and it should be the same. So this number is the same as this number. So it's kind of a logic of the whole linear layer in short. Then I use code from GitHub repository of PyTorch. So all the rights to this code belongs to Facebook, particularly Facebook AI team. And I modify it. As you see, it's very simple. We have inherit from optimizer. It's a SGD, and then we have parameters. This initializes our class. Then it goes step. So what it's doing is just like getting our parameters, our weight in our particular case, and getting the gradients, no momentum, no weight decay, as I know. And here is the simple calculation. So what I did here is I add some parameters here to check all the calculation. For example, P is our gradient. P is our gradient. P is our parameter. And dP is gradient. So this is the value of parameter. This is the gradient. This is I'm checking that it is. I wanted to check slope, so this is kind of the same as the slope, but anyway. And then we execute the cell. So here I'm checking the calculations, weights of the tensor after update, before update. So let's move forward. Optimizer detail. We instantiate this class. Calculate loss. Optimizer detail 0 grad. Loss backward. Optimizer detail step. So what we can see here. This is our parameter, weight before update. So it's these numbers. It's before update. Requires grad is true. Slope of the tensor. This. Running rate -1. Weights of the tensor after update. So it's a parameter containing these numbers. So after update, after we multiply it by what you multiply by, we got p data. So waits what the tensor after update. What the tensor after update. So we are following the optimizer logic, and we kind of a group LR minus group LR multiplied by gradients, and this is our result. And we add this data to our parameter, to our weights. So what is doing, like weight plus minus group LR multiplied by dp, and this is it. Here we are checking this logic. I clone this tensor, because if I didn't clone it, it will get updated and these values will be higher always. So let's check. So what we should check. So this is our weights before update. Then there is a slope. Then there is a learning rate. And then we have an update. So this update is pretty straightforward. This is this logic. And here I'm checking another way that we updated. So we have what I mean by this is that slope of the tensor, as we know from our lecture 1, that here we have a gradient that equals to x. So we have a slope that is equal to x. So if you look here, our x is minus 1, minus 0, 1, 0, 0, 2, 0, 3, and our slope is equal to these numbers. So, and then we multiply the slope by learning rate, and then we weight plus what we received from multiplying learning rate by the slope of the tensor. So slope of the tensor is 6. So everything is calculated correctly, and logic of PyTorch is pretty straightforward. So we received the right data and we check that, and everything is working fine. So we can see the loss, and that's it. So I hope this was useful. I hope this was interesting, because I'm doing my experiments. I'm kind of getting PyTorch and deconstructing it to understand it even better and even more. So I will have more videos on that for you. And if you have any questions and something else that you want to say to me, so feel free to email me or write a comment, and we will have a look. So I hope this was very, very, very interesting, and it opened your eyes for the new opportunities with this enormously good framework that is called PyTorch. Okay, all the good, all the best to you, and bye bye.